Hi, this is Srikanth as Assistant Professor of EEE Department. In this session, I am going to discuss the question bank problems on Module 3, that is Electrical Machines and Semiconductor Diodes. Here, a 25 kilowatt 250 volts DC shunt generator has armature field resistance of 0.06 ohms and 100 ohms respectively. Determine the total armature power delivered when working as a generator delivering 25 kilowatt output. Here the given data is the load power is 25 kilowatts, voltage 250 volts, armature resistance is given as 0.06 ohms, shunt resistance is given as 100 ohms. Now, if we take a shunt generator, this is the V, RA, EG, and this is RSH. This is the generated current, armature current IA. This is the load current. This is ISH. Here, armature current IA is equals to, according to Kirchhoff's current law, IA is equals to IL plus ISH. IA is equals to IL plus ISH. Load current is equals to PL by V, that is equals to 25,000 by 250, which is equals to 100 amperes. Now the shunt field current is equals to, shunt field current is nothing but shunt is directly connected in parallel to the voltage. So ISH is equals to V by RSH, which is equals to 250 by 100, which gives us the value as 2.5 amperes. Now let us calculate the armature current value. IA is equals to IL plus ISH, which is equals to 100 plus 2.5, 102.5 amperes. Now the induced voltage in armature EG is equals to V plus IARE, that is 250 plus 102.5 into 0.06, which is equals to 256.15 volts. Now the power delivered is equals to EG into IA, which is equals to 256.1615 into 102.5, which is equals to 26.25 kilowatts. So 1.25 kilowatts is the loss, because output we got only 25 kilowatts. The input which we are generating is 26.25 kilowatts. That is nothing but 1.25 kilowatts is the losses. Now, a 8-pole DC shunt generator with 778 wave connected armature conductors and running at 500 RPM, which supplies a load of 12.5 ohms resistance at a terminal voltage of 250 volts. The armature resistance is 0.24 ohms and the field resistance is 250 ohms. Find the armature current, induced EMF and flux per pole. Now the given data in the problem is the number of conductors is 778 conductors and the speed is given as 500 RPM and armature resistance is 0.24 ohms and shunt field resistance is 250 ohms and RL is equals to 12.5 ohms. Now the armature current is equals to IA is equals to IL plus ISH. Here shunt field current ISH is equals to V by RSH, because shunt field is connected in parallel with the voltage. In the parallel combinations, the voltage is same. So 250 by 250, which is equals to 1 ampere. Now the load current is equals to V by RL, which is equals to 250 by 12.5, which is 20 amperes. Now IA is equals to IL plus ISH, which is equals to 20 plus 1, 21 amperes. Now the induced voltage in armature EG is equals to V plus IA RA. That is 250 plus 21 into 0.24, which is equals to 255.04. Now the flux per pole. In order to get the flux per pole, we have to use the EMF equation of the DC generator. That is EMF equation EG is equals to phi ZNP by 60A. Here phi is equals to EG into 60 into A by P into Z into N, which is equals to, if we substitute these values, we are going to get the flux value as 0.00983. This we can also write it as 9.83 milliwebers. The next one is a 4-pole DC generator having wave wound armature, has 50 slots and 25 conductors per slot. Find the generated EMF. If it is driven at 25 RPM and the useful flux per pole in the machine is 0.03 webers. Now, this is for this problem, number of poles is given as 4 and flux is given as 0.03 webers and speed is 25 RPM and the number of parallel paths is, it is given wave wound. So number of parallel paths is equals to 2. Total conductors is equals to number of slots into conductors per slot, where Z is equals to 50 into 25, which is equals to 1250, where EG is equals to, we need to calculate. So EG is nothing but generated EMF, that is EMF equation of DC generator. EG is equals to phi ZNP by 60A. If we substitute, all the values are given. If we substitute all these values, phi is equals to 0.03 and speed is 1250 RPM and number of conductors is 1250 and number of poles as 4 and speed is 25 divided by 60 into, and number of parallel paths is given as 2. So the generated voltage is 31.25 volts. The next one is a 220 volts DC machine supplies 20 amperes at 200 volts as a generator. The armature resistance is 0.2 ohms. If the machine is now operated as a motor at the same terminal voltage and current, but with the flux increased by 10%, calculate the ratio of motor speed to the generator speed. So here we need to calculate the motor speed to the generator speed ratio, that is N2 by N1. Here the data which is given as DC generator armature resistance is 0.2 ohms, voltage is 200 volts, because these two values are same for the motor, which is motor and generator, because the same machine can work as a motor and generator in the case of DC machine. Here the flux increased in motor by 10% compared to the generator. So here phi 2 is equals to 1.1 times the phi 1. 1.1 times the phi 1. In case of generator, induced voltage in armature Eg is equals to V plus IARE, which is equals to 200 plus 20 into 0.2, which is equals to 204 volts. And in case of motor, EB back EMF is equals to V minus IARA, that is equals to 200 minus 20 into 0.2, which is equals to 196 volts. Now the turns ratio N2 by N1 is equals to E2 by E1 into Phi2 by Phi1. So here E2 by E1 we have calculated, that is 196 by 204 into Phi2 by Phi1 is equals to Phi2 value is 1.1 times of Phi1 by Phi1. Here Phi1 will get cancelled. We are going to get the value as 0.87. This is the ratio of speeds when it is acting as a motor and generator, N2 by N1. The next one is a 440 volts DC shunt motor takes a no load current of 2.5 amperes. The resistance of shunt field and the armature are 550 ohms and 1.2 ohms respectively. The full load line current is 32 amperes. Find the full load output and the efficiency of the motor. Here the given data, voltage is given 440 volts. No load current is given as 2.5 amperes and armature resistance is 1.2 ohms and shunt field resistance is 550 ohms. Full load is given as 32 amperes. We need to calculate what is the output power and efficiency. So here input power is equals to, first this is a motor, so we are going to have the electrical power as input. So the input power is equals to 440 into 32 load current, full load current, that is equals to 14,080 watts. That we can also write it as 14.08 kilowatts. Here, when there is no load, whatever the input which we are providing, that is going to be wasted in the form of heat in the armature conductors. So that is nothing but losses in the machine. So the losses in the machine is equals to 440 into 2.5, which is equals to 1100 watts. Now efficiency is equals to output power by input power. So here efficiency is equals to output power by input power. So here output power is equals to input power minus losses. Input power minus losses, which is equals to 14,080 minus 1100, which is equals to 12,980 watts. Now this is the output power which we got, and here the efficiency is equals to input power minus losses by input power, which we are getting it as 92.18%. The next one is a 3-phase 20 HP 208 volts 60 Hz 6-pole star connected induction motor delivers 15 kilowatts at a slip of 5%. Calculate synchronous speed, rotor speed and frequency of rotor current. So here the given data is number of poles is 6, frequency is 60, slip is 5%. Here the synchronous speed is nothing but it is the speed at which the rotating magnetic field is going to rotate. That is Ns is equals to 120 F by P, which is equals to 120 into 60 by 6, which is equals to 1200 RPM, where Nr is equals to 1 minus S into Ns, which is equals to 1 minus 0.05 into 1200, which is equals to 1140 RPM. Now Fr is equals to S into Fs, which is equals to 0.05 into 60, which is equals to 3H. Now these are the problems on diodes. An AC supply of 230 volts is applied to a half wave rectifier circuit through a transformer of turns ratio 10:1. Find the DC output voltage and peak inverse voltage. Assume the diode to be ideal. The given data VRMS is equals to 230 volts. Armature resistance is 0.06 ohms. Turns ratio is N1 by N2, which is equals to 10. Where VDC is equals to, we need to calculate, and peak inverse voltage we need to calculate. Here primary to secondary turns ratio is 10:1, and the RMS primary voltage is 230 volts. The maximum primary voltage will be equals to root 2 times the VRMS, which is equals to root 2 into 230, which is equals to 325.3 volts. And maximum secondary voltage Vs max is equals to Vp max into N2 by N1, which is equals to 325.3 into 1 by 10, which is equals to 32.53. And here IDC is equals to Im by pi, where VDC is equals to Im into RL by pi, which is equals to Vs max by pi, which is 32.53 divided by pi, which is equals to 10.35. This is the DC output voltage. And the peak inverse voltage is nothing but it is the maximum voltage which can withstand in the reverse bias condition. That is nothing but in the negative half cycle, what is the peak which we are going to get? That is nothing but the same as the positive peak, that is 32.53 volts. Now a half wave rectifier is used to supply a 50 volts DC to a resistive load of 800 ohms. The diode has a resistance of 25 ohms. Calculate AC voltage required. The given data output DC voltage is 50 volts and diode resistance is 25 ohms. Load resistance is 800 ohms. Now when we have these are the values, VDC is equals to whatever the maximum current into RL by pi, that is equals to Vm into RL by pi into Rf plus RL. Im is equals to Vm by Rf plus RL. If we substitute these values, 50 is equals to Vm into 800 by pi into 825. From this, if we are going to get Vm value as 162 volts. Hence, an AC voltage of maximum value which is required for the given data is 162 volts. Now, a full wave rectifier uses two diodes. The internal resistance of each diode may be assumed constant at 20 ohms. The transformer RMS secondary voltage from center tap to each end of secondary is 50 volts and the load resistance is 980 ohms. find the mean load current and RMS value of load current. So here the given data is VRMS is given as 50 volts and the diode forward resistance is 20 ohms and load resistance is given as 980. Here IM is equals to VM by RF plus RL, which is equals to 70.7 by 20 plus 980, which is equals to 70.7 milliamperes. The mean load current IDC is equals to 2 into IM by pi, which is equals to 2 into 70.7 by pi, which we are going to get it as 45 milliamperes. And RMS value of load current is equals to IM by root 2. Here the IM value which we got it is 70.7 divided by root 2, which gives us the 50 milliamperes. Here an AC supply of 230 volts is applied to the bridge type rectifier through a transformer of turns ratio 4:1 and the load resistance is 200 ohms. The diodes are assumed to be ideal. Find DC output voltage, peak inverse voltage, output frequency. Here the given data turns ratio is 4:1. RMS primary voltage is 230 volts. RMS secondary voltage is 230 into N2 by N1, that is equals to 230 into 1 by 4, that is 57.5 volts. Here the maximum voltage across the secondary is V maximum, which is equals to 57.5 into root 2, that is equals to 81.3 volts. The average current IDC is equals to 2 Vm by pi, where RL is equals to 2 into 81.3 by pi into 200, which is equals to 0.26 amperes. And DC output voltage VDC is equals to IDC into RL, which is equals to 0.26 into 200, which is equals to 52 volts. And the peak inverse voltage is equal to the maximum secondary voltage, that is 81.3 volts. In full wave rectification, there are two output pulses for each complete cycle of input AC voltage. So in full wave, we are going to have the two positive half cycles in one complete half cycle. So the F output is equals to 2 times the F input, that is equals to 2 into 50, that is 100 Hz. The next one is a half wave rectifier has a load of 3.5 ohms. If the diode resistance and secondary coil resistance together have a resistance of 800 ohms and the input voltage has a signal voltage of peak value 240 volts, solve peak, average and RMS values of current, AC input power, DC output power and efficiency. Here the given data, the load resistance is 3.5 kilo ohms, RS plus RF is equals to 800 ohms and VM is equals to 240 volts. The peak value of current IM is equals to VM by RL plus RS plus RF, which is equals to 240 by, here RL plus RS is 800 plus 3500. This is 3.5 kilo ohms. So which is equals to 55.81 milliamperes. The DC output voltage VDC is equals to IDC into RL, which is equals to 0.26 into 200, which is equals to 52 volts. and the average value of DC current IDC is equals to Im by pi, which is equals to 17.77 milliamperes. And the RMS value of current IRMS is equals to Im by 2, which is equals to 27.9 milliamperes. Here DC output power PDC is equals to IDC square into RL, which is equals to 1.105 watts. And the next one is AC output power, which we need to calculate, that is equals to IRMS square into RF plus RL plus RS, which is equals to 27.95 into 10 to the power of minus 3 whole square into 3500 plus 800, which is equals to 3.348 watts. And efficiency is equals to PDC by PAC into 100, that is equals to 1.105 by 3.348 into 100, which is approximately 33%. And here the resistance, load resistance value is 3.5 kilo ohms. In this session, we have discussed the problems on DC machines, AC machines, and diodes. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.